Welcome to today's Explainer. Today, we're looking straight at our planet's massive, invisible shield against global climate shifts. And yeah, you guessed it, we're talking about the ocean. We're going to break down exactly how this vast body of water is fundamentally transforming, tracing the chemical domino effect from the massive, global macro level right down to the local impacts happening just off our coastlines. You know, we often think of climate change as something happening way up above our heads in the atmosphere. But honestly, some of the absolute most profound changes are actually happening right below the surface. So we're going to pull back the curtain on this invisible dynamic and explore how atmospheric changes combine with everyday coastal activities to totally reshape our seas.
Okay, let's dive into this with a number that is absolutely crucial to anchor our understanding: 1/3. A staggering 1/3 of all carbon dioxide produced by anthropogenic or human-driven activities is absorbed right into our oceans. I mean, just think about that sheer volume for a second. The ocean is basically acting as a giant sponge, serving as an absolutely essential climate buffer for our planet. Without this massive aquatic reservoir taking in that much CO2, the climate change we experience up in the atmosphere would look drastically different. But of course, this immense buffering service doesn't just happen like magic, and it certainly doesn't come without a physical cost to the water itself.
And, well, that physical cost is ocean acidification. Mechanically speaking, this is a literal change in ocean chemistry. We're talking specifically about the lowering of pH and an increase in hydrogen ions, and this is driven directly by the ocean's massive uptake of those atmospheric carbon compounds we just talked about. The crazy thing is, this isn't something you can just see with the naked eye when you're standing on the beach or looking over the bow of a boat. It is a profound, completely invisible chemical transformation happening right beneath the waves, continuously across the entire globe.
Now, what's really interesting about this breakdown is tracing the exact chemical chain reaction at a microscopic level. As atmospheric CO2 uptake increases, it literally forces the concentration of hydrogen ions in the water to spike. And because of that sudden chemical shift, the concentration of carbonate ions drops, which inevitably forces the overall pH of the ocean down. It's an undeniable sequence happening billions of times over every single second. It is basically basic chemistry playing out on a planetary scale. The more carbon that enters the system, the more the hydrogen ions increase, directly stripping away those crucial carbonate ions and driving the pH lower and lower.
So why does this specific sequence matter so much to us and to the planet? Well, it's because the oceans are becoming fundamentally less alkaline. That is the crucial takeaway from this macro-level view. The very chemical baseline of this vast global reservoir, an environment that marine life has spent millions and millions of years perfectly adapting to, is shifting away from its natural, slightly alkaline state. The foundational chemistry of our planet's largest ecosystem is quite literally being rewritten by the atmosphere.
But you know, the story doesn't just end with the global atmosphere. We really need to shift our focus now from that vast global macro level right down to the specific local level. Because while atmospheric carbon uptake is undeniably changing the entire global ocean, smaller scale, regional human activities are also severely altering ocean chemistry right in our own backyards. It's a localized effect that heavily compounds the global issue, and it's driven by very specific, tangible things we do on land every single day.
Which brings us to the first of our local accelerants, acid rain. Now get this, acid rain can have a severely low pH, landing anywhere between 1 and 6. And for a little context on just how extreme that is, a pH of 1 is roughly equivalent to battery acid. So when precipitation that remarkably acidic falls over the ocean, it doesn't just instantly dilute and disappear without a trace. No way. It directly impacts the surface ocean chemistry right where it lands. It is literally raining acid into the top layer of the sea, creating an immediate measurable chemical shift in that specific, localized area.
And this brilliantly illustrates a fascinating contrast in scale. While acid rain has a major effect on ocean chemistry locally and regionally, right where a heavy acid storm passes, its global effect is actually very small compared to atmospheric CO2. It isn't shifting the baseline pH of the entire global ocean in the same way, but instead, it acts as an intense focal point, creating severe, localized pockets of coastal and regional acidification that local marine life definitely has to contend with.
Beyond acid rain, our coastal waters are heavily affected by another local factor, and that's eutrophication. This whole process starts with excess nutrient inputs, primarily nitrogen, and these nutrients, they come directly from our land-based infrastructure, specifically runoff from agriculture, the heavy use of fertilizers, and inputs from sewage systems. When these standard byproducts of modern food production and human waste management wash off the land and reach our coastal waters, they act as a massive, unintended fertilizer for the ocean.
Let's move to Tenali and see how this builds into a wild biological domino effect, where biology forcefully alters chemistry. That sudden influx of excess nitrogen triggers massive algae and plankton blooms. The marine organisms absolutely gorge on the nutrients. But inevitably, these giant blooms collapse, they die off and sink down to the seabed. As bacteria begin decomposing all that dead organic matter, their intense respiration literally sucks the oxygen out of the surrounding water. This causes a drastic drop in oxygen and a simultaneous huge spike in CO2, which, as we established earlier, directly drops the pH. So local nutrient boost ultimately suffocates the water and spikes its acidity.
So the crucial point is that ocean acidification is a dual threat. It's a squeeze coming from two completely distinct directions. On one hand, we have global atmospheric emissions fundamentally changing the baseline chemistry of the ocean from above. On the other hand, we have local runoff, like highly acidic rain and nutrient-driven eutrophication, intensifying and compounding that acidification right along our shores. It is an intricate combined mechanism that is continuously lowering our oceanic pH.
Which leaves us with this final, pressing question. We've seen the chemistry, we've seen the global scale, and we've mapped out the local impacts. With our oceans absorbing massive global emissions from above and continually taking in local runoff from our coasts, how much more can this vital reservoir take? It's a reality occurring entirely out of sight, yet it is fundamentally reshaping the largest ecosystem on Earth. Thank you so much for joining me for this explainer, and I really hope this leaves you eager to look deeper into the incredible, shifting chemistry of our seas.